And just like when you talk about compound words are two words put together to make one word. A compound event is when you try and find the probability, or compound events is when you put two events together. So therefore, when we find the probability of compound events, we're going to find the probability of two or more events. Let's look here. We have two types of, actually we have four types, two types on this screen. The first one is independent events. And here's the formula. Keyword is the probability of event A happening and event B happening. So we're trying to find a probability that both events will happen. What you do is you take the probability of the first event and you multiply it by the probability of the second event. So in this example we have, if a bowl contains 4 apples, 3 bananas, 4 oranges, and 2 peaches, what is the probability of choosing a banana, putting it back, and then choosing an orange? Well, we want to find the probability of a banana, and then an orange. And why is this independent? It's independent because we put it back. It's independent because we put it back. Pay attention. It says the probability of choosing a banana and then choosing. But look at the formula. The formula says and right there. So this is the reason why we will be using independent events. All right, so the probability of a banana goes first, and we're going to multiply it by the probability of an orange. And so this is going to equal the probability of a banana. There are 3 bananas. Out of 4 plus 3 is 7, plus 4 is 11, plus 2 is 13. 3 out of 13. We're going to multiply the probability of a banana by the probability of an orange. And remember that we pulled the banana out and we put it back, so there are still 13 fruits in the bowl. And how many oranges are there? There are 4 oranges. And when you multiply those, 12 out of 169. And go ahead and change that to a decimal and then a percent. You change that to a percent. You should get something that is close to 7.1%. 7.1%. Let's look at the next example on dependent events. Dependent events. It says the probability of A and B, so we're also having both events occur. It's equal to the probability of A happening times the probability that B happens given, that's what that line means, given that A has already occurred. And what does that mean? Well, look in this situation. In this situation, you're going to eat a piece of the fruit. So then that's going to change the probability of choosing an orange second. So let's go ahead and talk about that. That's what this probability means. This probability of B given A means that the probability B given A, the probability that an orange is chosen given that A has already happened. Let me see if I can clarify that when we work out the example. So we say the probability of a banana and an orange is equal to the probability of a banana. It's the probability of a banana. Let me spell it right this time. Times the probability of an orange, given that you've chosen a banana already. And so let's look at the probabilities here. If it's the same example as before, if a bowl contains 4 apples, 3 bananas, 4 oranges, and 2 peaches, what is the probability of choosing a banana, eating it? And that's the only difference as the example above. You eat it, and then you choose an orange. So you're going to be eating 2 pieces of fruit here, or you're actually choosing 2 pieces of fruit. Well, the probability of a banana is 3 out of 13, and that's the same as before. And an orange, there are 4 oranges, but now pay attention. Remember, you ate the banana, so there are only 12 pieces of fruit in the bowl. There's only 12 pieces of fruit in the bowl. And so when you multiply, you get 12 times 156. I'm sorry, 12 divided by 156. So now when you go ahead and divide this out, you should get something like 7.7%. Not much of a difference between the two examples, but there is a little bit of a difference. A little bit of a difference. So those are the first 2 examples. Independent events, dependent events. The next 2 we're going to talk about is mutually exclusive. Mutually exclusive. All right, mutually exclusive events. This is the probability of A or B occurring. And what this means is that you are going to be trying to get one of the events to happen. Not necessarily both of them. You're trying to get one of the events to happen. The probability of A or B is equal to the probability of A plus the probability of B. So for this example, on a number cube has the numbers 1 through 6 on it. On a number cube, what is the probability of rolling an even number or rolling a 5? Now, you're trying to get an even number or a 5. You're not trying to get both events. You're trying to get one or the other one, not both of them. So the probability of an even number or a 5, that's that part right there, is equal to the probability of event A, which is an even number, plus the probability of event B, which is a 5. I made a list for you over here on the left side of the screen. Even numbers on a number cube are 2, 4, and 6. So how many even numbers are there? There are 3 even numbers out of how many total numbers? 6. Now the probability of a 5, a lot of people will put a 5 on top because they see 5. And that number 5 does not occur 5 times. How many times do you see the number 5 on a number cube? You only see it once. You only see it once. And so therefore, when you add those 2 fractions, you're going to get 4 over 6, which is 66.7%. It reduces to 2/3, which is 66.7%. If you want to quickly do that one in your head. And the next type of compound event is overlapping events. Now this one is where, let's look at our example real quick and then we'll come back to the formula. It says on a number cube, what is the probability of rolling an even number or rolling a 4? And if we notice in our even number list, 4 is already in there. 4 is already in there. So what's the probability of getting an even number or a 4? So we're still only trying to get one thing to happen. It's either even or it's a 4. But let's look at our formula. The probability of A or B happening is equal to the first event, the probability of the first event, plus the probability of the second event. But we have to subtract out what they have in common. And in this case, what they have in common will be rolling a 4. Okay. So let's look here. The probability of an even number or a 4 is equal to the probability of an even number plus the probability of a 4 minus the probability that you get an even number and a 4 on the same rule. So the probability of an even number is still the same. There are 3 even numbers out of 6. The probability of a 4, there is 1 4 out of 6 minus how many even numbers are 4 on a number cube? Well, there's one even number that is also a 4, and there are 6 total numbers. And we subtracted out that even 4, that even number of 4. So if we look, 3 over 6 plus 1 over 6, that's 4 over 6. And then minus 1 over 6 is 3 over 6. And that is equal to 50%. These numbers here will not always be the same. In this case, they happen to be the same. This was a quick example. I think you guys can see a number cube in your mind, and you can visualize this happening. But in every example you do, those numbers will not always be the same. They just happen to occur the same here. All right, let's move on. Let's move on to some problems here that you can try and work on your own. If you feel confident enough with these, you pause the video, work them out, and try and get the correct answer. Let's read through this problem. Jenny rolls a cube numbered 1 through 6 and flips a coin. So there are 2 events happening. She's rolling a cube, and then she's flipping a coin, and here's the key word, and. Okay, she's trying to get both events to occur, not just one of them. This is not an or problem. This is not mutually exclusive or overlapping. This is and. So this is either independent or dependent. What is the probability of rolling an even number and flipping tails? So the probability of an even number and flipping tails, we're going to multiply those. This is going to be an independent event because rolling an even number on the number cube is not going to affect us getting a tails on a coin. Probability of an even number, this was the example in the last problem. 3 even numbers out of 6. And we're supposed to multiply tails. There is 1 tail on a coin out of 2 sides. And we assume that it's a fair coin, that heads and tails are on both sides, not tails on both sides or not heads on both sides. So we assume that it's a fair coin and a fair number cube also. So we have 3 over 6 times 6 over 2. And remember, multiplying fractions, you multiply straight across. So you're going to get 3 out of 12, which we know reduces to 1/4, and 1/4 is 25%. So she has a 25% chance of rolling an even number and then flipping tails on a coin. This next one. Without replacement, Eric picks 2 marbles from a basket containing 14 white marbles and 6 yellow marbles. What is the probability that he picks 2 yellow marbles? So without replacement means that he's going to choose one and then not put it back. And remember, he's picking 2 marbles. So if he's picking 2 marbles, we know that that's either independent or dependent, because there are 2 events happening. And this without replacement means that the probability of getting the second yellow marble is going to be affected by the probability of not replacing the first marble. So let's look here. Without replacement. So we should say the probability of yellow is being multiplied by the probability of yellow, given that you've already pulled a yellow marble out. And so now when we look here, the probability of yellow marble, there are 6 yellow marbles. And if there are 14 white, 6 yellow, there were 20 total marbles. We're going to multiply that by the probability of a yellow marble. Now remember, Eric did not put the marble back, so there are not 6 yellow marbles anymore. There are 5 yellow marbles. And there are not 20 marbles in the basket. There are 19. And so that's what this bar means in your formula. What's the probability that the second marble chosen is yellow, given that you've already pulled a yellow marble out of the basket? And so when we multiply these, 6 times 5, 6 times 5 is 30. And 20 times 19, I believe, is 380. And just a quick canceling, you can reduce each one of those numbers by 10. So you know that you have 3 divided by 38, or 30 divided by 380, but once you reduce each one by 10, 3 divided by 38, if you can't do that in your head, that'll be less buttons you will have to push on the calculator. And so now we're going to get 7.9%. So there's a 7.9% chance that Eric pulls 2 yellow marbles out of the basket. This next one we talk about, one card is to be drawn from a standard deck of 52 cards, so find the probability of each card being drawn. So let's find the probability of a king or a queen being chosen, and this word "or" is the key. If you look back into your formulas, mutually exclusive and overlapping events, they use the word "or" in their formula. So therefore, their formulas say we have to find the probability of a king and add it to the probability of a queen. And that will get our solution here. That will get our probability. And remember, they want a probability of a king or a queen being chosen. But remember, this "or" means that we only have to pull one of those cards out, not both of them. We're trying to only get one of them out. Probability of a king. Well, if we look, let me use a different color so you can see it. How many kings are in the deck? There are 4 kings. And how many cards? 52. 4 out of 52. We're going to add that to the probability of a queen. Well, queens are right beside the kings. There are 4 queens in the deck out of 52. When we add these together, remember you have to have common denominators. So that common denominator is 52. And so let's add the top 2 numbers since they already have a common denominator, and that will be 8. 8 divided by 52 is the probability of choosing a king or a queen. And when we change that to a percentage, we're going to get 15.4%. And you notice I am rounding all these to 1 decimal place. 1 decimal place. And you could probably be using the approximately symbol there because it's not exactly 15.4%, it's approximately. Let's move on. What's the probability of a jack being chosen or a spade being chosen? So if we look, there's a jack, and here are all the spades. And since the word or, we know that this is either going to be mutually exclusive or overlapping. And if we look at what I've done up here, I've kind of already surrounded the two types of cards that we're trying to choose. But look at this one right here. That jack right there, that would be the jack of spades. The jack of spades is part of pulling a jack, and it's also part of pulling a spade. So this is going to be an overlapping event, which says we want the probability of pulling a jack added to the probability of a spade, and then we're going to subtract the probability of the jack of spades being chosen. Probability of the jack of spades being chosen. And I know in your formula the word and was right here. But we never say it's the jack and a spade. We say the jack of spades when you are working with cards. So let's go ahead and figure out those probabilities. How many jacks are there? There are 4 jacks out of 52 cards in the deck. Now remember, you're only going to be pulling 1 card out because this is or. You're not pulling both of them out. You're only pulling 1 out. So we're going to add it to the probability of a spade being chosen. How many spades are there? There's the ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. So right there's 10 cards. There's 11, 12, 13. 13 spades out of 52. And I wanted to let you know that there was only one thing being chosen because that number on the bottom does not change in this case. And now we're going to subtract. Well, we know the total cards is 52. How many jack of spades are in the deck? Well, I have it circled up here in yellow. Let me go ahead and circle it in green. There is 1 jack of spades out of 52. And that's the number that we have to subtract out. And that's because the jack of spades is in that probability and the jack of spades is in that probability. It's in there twice, so we have to pull out 1 of them. That way it's really only in there once. And so let's add these numbers up. 4 plus 13, and we know they all have common denominators. So let's go ahead and add up the numerators. 4 plus 13 is 17 minus 1, and that's 16. 16 over 52. And 16 over 52, 16 over 52 is approximately 30.8%. It's approximately 30.8%. So the probability of getting a jack or a spade is going to be 30.8%. This next one, probability of a number card or an ace. Probability of a number card. 2 through 10. Those have numbers on them. And then ace. There are 4 aces. So the probability of a number card. Well, we know that this is an or in here, so we're only going to be trying to get one of those in one pool. The probability of a number card or an ace. We only have one event here. And so that's going to be mutually exclusive or overlapping. That's what the formulas say. The formulas use the word or in those two events. And are there any aces that are also number cards, or any number cards that are also aces? And that would be a negative. So therefore, this is mutually exclusive. And we just add those two probabilities together. How many number cards are there? Well, if we look in the clubs, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 number cards, and there are 4 suits. So 9 times 4 is 36. 52 cards in the deck. And how many aces? 1, 2, 3, 4 aces out of 52. We know the denominators are the same. So let's add the numerators. 36 plus 4 is 40. And so when we find that as a percentage, it's going to be approximately equal to 76.9%. So say it's a likely chance of getting one of those two, a number card or an ace. But 76.9, that's a pretty good chance of it happening. Almost twice as better as a jack or a spade, and quite a bit better than a king or a queen. So, and this last one, what's the probability of a jack or a queen? We know the key word there is or, so we're only trying to get one of them. And let's look at the jacks. Here's the jacks. Here's all the queens. So we know that there's no jacks that are also queens, no queens that are also jacks. So this is mutually exclusive. They do not share any events in common. Probability of a jack is going to be 4 jacks out of 52. There are 4 queens out of 52 cards. And that's going to be 8 out of 52. And I believe 3 examples ago, we had one that was 8 out of 52. And I think that was about 15.4%. 15.4%, 8 out of 52. So, and that, remember, that was this is the same probability of a jack or a king. And if you notice, this number here is an 8. Can you count these up here? How many jacks and queens do you have? There are 8 cards there out of 52. So the probability of a jack or a queen being chosen is 8 out of 52, or approximately equal to 15.4%. Back to these type of problems, you have a bag of marbles that has 2 purple marbles, 3 red marbles, and 4 blue marbles. 3 marbles are drawn at this time. Okay, so this is a little different than what we've done before, but it's still one of those types of problems. 3 marbles are drawn with replacement. What is the probability that a red and a blue marble are drawn. That's the key word, and. So we know that's either independent or dependent. And if we notice that what does it say? Oh, right here. With replacement. So therefore, when you pull a marble out of the bag, you'll put it back. You pull a marble out of the bag and you put it back. And I've only chosen red and blue. So therefore, let's go ahead and change the problem to say two marbles. And that still doesn't change any of our thought process up to this point. So two marbles are drawn with replacement. What is the probability that a red and a blue marble are drawn? Well, since we're replacing it, it is going to be an independent event because the probability of the second event, the probability of a blue marble being chosen, is not affected by choosing a red marble first. The probability of red marble being chosen, 3 red marbles out of how many total? Well, there's 2 and 3 make 5, and 4 more makes 9. So that would be 3 out of 9. 3 red marbles out of 9. We're going to multiply it by the number of purple marbles. We notice 2 purple marbles out of 9. So let's go ahead and multiply those. 3 times 2, it's multiplication. We multiply straight across, both top and bottom. 3 times 2 is 6, and 9 times 9 is 81. And so when you find the percentage of that happening, you're going to get something approximately equal to 7.4%. Approximately equal to 7.4%. Let's look at this example. Jason has a bag full of jelly beans that he intends to eat as he watches TV. The bag contains 5 white, 1 black, 6 green, 4 pink, and 2 yellow jelly beans. What is the probability that he will eat a white jelly bean followed by a black jelly bean? Well, we can't look for those keywords of and or to determine whether it's mutually exclusive or overlapping or independent, dependent. But let's think about the situation here. What's the probability that he will eat a white jelly bean? So he's trying to get a white jelly bean followed by a black jelly bean. So he's trying to go white jelly bean, black jelly bean. He's trying to get both of them. White jelly bean and black jelly bean. So if he's trying to get both of them, that would be 2 events occurring, and 2 events occurring is either independent or dependent event. And so that means that you're going to be multiplying the 2 fractions. Now you need to determine whether it's independent or dependent, because if he eats a white jelly bean, the probability of getting a white jelly bean is going to affect the probability of pulling out a black jelly bean second. So therefore that is going to be a dependent event. And we say the probability of a white jelly bean multiplied by the probability of a black jelly bean given that you've already had a white jelly bean. And so let's figure out these probabilities. What's the probability of a white jelly bean? Well, there are 5 white jelly beans. So there are 5 out of how many? Well, there's 5. 1 more makes 6. 6 more makes 12. 4 more makes 16. And 2 more makes 18. And so that's the probability of a white jelly bean. What's the probability of a black jelly bean? Right here. one black jelly bean. So there's only one black jelly bean out of how many total? Well, let's pay attention that he ate the white one already. So how many jelly beans are in the bag? 17 of them. 17 are. And that's the independent event right here. That's this probability is called the conditional probability. Given, what's the probability of a black jelly bean given that a white jelly bean has occurred? It's going to be 1 out of 17 because we've already eaten the white jelly bean. Or Jason has already eaten that white jelly bean. So let's go ahead and multiply these. On the top, when you multiply 5 times 1, you're going to get 5. And on the bottom, when you multiply 18 times 17, you get 306. And let's figure out what that percentage is. That's going to be 1.6%. 1.6%. So the probability of him choosing a white jelly bean and then choosing a black jelly bean is highly unlikely to happen. Let's look at this next example. You have in a bag of 2 red marbles, 3 white marbles, 5 green marbles. What is the probability that you will draw a marble that is red or white? And that's the key word, or. So that's going to be either mutually exclusive or overlapping events. So you need to determine which one. Can you have a red marble that is also a white marble? And if we look, it doesn't look that way because we only have red, white, and green. Those are the only 3 types of marbles in the bag. And I know there are some red marbles that have a white, to them, and there are some white marbles that have red to them that would fit in this category. But we're not talking about that right now because there's only red, white, and green in our situation. And I think if we were talking about those marbles that were multicolored, we'd probably say like there were 6 red, white marbles, and they would be specific marbles of red, white. That's what we would call those. So anyways, so since we know that they have no events in common, that would be mutually exclusive. So we just find the probability of a red marble being chosen plus the probability of a white marble being chosen. Probability of red, there are 2 red marbles out of 2 plus 3 is 5, plus 5 more is 10. 2 red marbles out of 10 total marbles. The probability of white marbles, there are 3 white marbles and 10 marbles in the bag. And we're trying to only get a red or a white marble. So we're only trying to get one, we're only pulling one marble, and we're trying to make it either red or white. And we know that they have common denominators already. So add the top numbers. 2 plus 3 is 5. And we know that this is exactly 50%. Exactly 50%. All right, so let's go from here. Same type of question with one word that's a little bit different. Actually, it's the same exact question. And let me read through this quickly. In a bag of 2 red marbles, 3 white marbles, 5 green marbles, what is the probability that you will draw a red marble? Or I'm sorry, let me read that sentence again. What is the probability that you will draw a marble that is red and white? So if we look at this, what is the probability that you will draw a marble that is red and white. So if you come and look at this problem, we're trying to go red and white. We need to change this up a little bit because we need to say that you're going to draw, that you will draw two marbles. What is the probability that you'll draw two marbles with the first one being red and the second one being white? So, probability of a red one being chosen times the probability of a white one being chosen, and we're multiplying these because the word and signifies that we're having two events occur. They were trying to get a red marble and then a white marble after that. It doesn't say you're not replacing, so let's go ahead and say that. What is the probability that you draw a red and a white marble without replacement? Without replacement. And so that changes this to say what is the probability of a white marble given that a red marble has already occurred, or that you've already pulled out a red marble. Probability of a red marble, 2 out of 10, times the probability of a white marble given that you've already chosen a red marble. Well, there are 3 white marbles and only 9 of them left in the bag because you pulled out the red marble and didn't put it back. Multiply the top numbers to get 6 and multiply the bottom numbers to get 90. And 6 divided by 90 is going to give you approximately 6.7%. So the probability of pulling out a red marble and then pulling out a white marble without replacing the first one is 6.7%. And let's look at this last one here. Georgia keeps her chalk in a box. She has 5 pieces: a purple, a green, a red, an orange, and a blue. If she randomly takes one piece out and then returns it and takes another, what is the probability that both times she will take out the orange piece? Let's say, for example, she's trying to choose one of the other colors. What's the probability that she pulls out both of them are going to be orange? Well, let's think about this. She's going to be pulling out 2 pieces of chalk. So if she randomly takes one piece out and takes another piece out, so there are 2 pieces of chalk being chosen, and what's the probability that they're both orange? Well, if there are 2 pieces of chalk being chosen, it's either independent or dependent, but because she returns the first piece, this is the reason why it is independent. So the probability of an orange piece of chalk is going to be multiplied by the probability of an orange piece of chalk being chosen. Probability of an orange piece of chalk, well, there are 5 pieces total. 1 of them is orange. 5 pieces total, multiplied by, remember, she returned the first piece, so there's still 1 piece of chalk in there that is orange, and there are still 5 pieces of chalk in the box. Multiply the top numbers. 1 times 1 is 1. Multiply the bottom numbers. 5 times 5 is 25. And this is equal to 4%. So the probability that she pulls out 2 pieces of chalk and it is orange both times is 4%. That's all we have here on finding probability of compound events. If you have any questions, let me know the next time you see me.